So in the last few videos we've been talking about the membrane equation and the intrinsic properties of biological membranes. And in this video I want to extend that discussion to consider what happens when current is applied to a cellular membrane. And this can happen quite often in the lab. So in this schematic figure here we have a spherical cell or neuron, and as we talked about in the previous video, the membrane is modeled as a capacitor and a resistor in parallel. And the new addition is this micropipette electrode, which, when stuck into the cell, can either push positive charges into the cell, or negative charges into the cell, or positive charges out of the cell. Sort of depends on exactly what solution you're using. But the details of this don't really matter. But the point is that you can either put in or take out electrical charges from the intracellular cytoplasm of the cell, and this means that you can influence the cellular membrane potential. So how do we actually influence the cellular membrane potential? Well, this second schematic down here shows the equivalent electrical circuit for this idealization that's shown in the first figure. So what is this showing us? Well, in the previous videos we've been talking about a simple circuit that describes the cellular membrane, and I've just circled it in blue. So you have the capacitor and the resistor, and then some sort of electrical potential that is built up by the sodium-potassium pump and asymmetric distribution of ion concentrations across the cell membrane. So those three components in the circuit we've already talked about, and now I just want to add one further component, which is this current source. Here it's an ideal current source. So this isn't a big addition, and there's no reason why we can't mathematically incorporate this into our model that we've been talking about, and that's exactly what we're going to do in this video. So previously we've talked about how all the currents within this electrical circuit need to sum to zero, and that's the conservation of current, or it's called Kirchhoff's law. So we're going to build another mathematical model on this same basis. So before, when we were looking at this law, we had only two currents we had to consider. We had to consider the capacitive current, which we derived from the law of capacitance, and the current flowing over the resistor, which we used Ohm's law to derive. And now we have a third current to consider, which is this ideal current source, or the current flowing through the pipette here. And immediately what you'll notice is that while I was adding these two currents, I am subtracting the injected current. And this might seem sort of strange to you. Why would I be subtracting this current when I'm adding the other two? And I'm not going to get into this too much, because honestly this is just a convention. There's no reason why we couldn't make this a plus sign. It's just a convention that gives us properties that we tend to like. And this is the convention that, if you use this sign convention, it ends up meaning the following. It means that if you add a positive current into the cell, so if Ij is positive, then this implies that the membrane potential will increase, which is also known as depolarization. You'll depolarize the cell membrane, or increase Vm, make it more positive. And conversely, if Ij is negative, which would then make this positive, negative minus negative, then this implies that Vm is decreasing. So this is the sign convention that is used, and when you use this sign convention, it turns out that you need to subtract rather than add the injected current, as you see there. One thing that I should mention before going on, actually, is that this convention only applies to current from a directly applied current from an electrode. It actually will not hold if the current is generated by an intrinsic membrane conductance. And that might not make sense to you now, but later I'll explain that again, and you'll realize that this convention is actually somewhat different in different circumstances. So in this next step, I've just added what we already know. The capacitive current is given by this expression, which I've already shown in a previous video. The the current across the resistor is given by this expression, and I've just brought the injected current over to this side. So now I've just simplified this a step further. As before in the previous video, tau is equal to R times C, and the only difference from this and the previous video is that VSS has changed, which makes sense. So the steady-state membrane potential depends on the amount of injected current and is also depends on the resistance of the member potential or the input resistance. So this explains how the injected current affects the steady state voltage, and other than that, the system is going to evolve the same way. So that's pretty much it for this video. I just wanted to quickly show you what happens when you add an injected current into this system, and it turns out that it doesn't change the overall dynamics or the properties of the dynamical system. It just affects what the steady state voltage is going to be. So in the next video, I'll actually cover in detail how changing the level of the injected current changes the dynamics of the system. But hopefully you can already sort of guess what's going to happen, because all that the injected current does is change where the steady state voltage is going to be. So thanks for watching, and I'll see you in the next video.